All right, what's up, everyone? Welcome to week 31 of Chill Kernel Hacking for Fun. This week we're looking into Lab 4, Preemptive Multitasking. We're going to be doing some pretty neat stuff involving figuring out how to bring up the other processors on a multi-core system and so the OS can make use of them and run code on them and stuff like that. Right on. So just a note about the organization of the videos. So I will actually be going on a trip for a few weeks for the next 3 weeks. So what I've done is pre-recorded a couple streams, which will go out in the next couple weeks. Hey, what's up, Afnan? Test 1, test 2 in the chat. Yeah, I've pre-recorded a few streams. So this stream, I'm a bit forward into the future. And so if you've been watching all the streams, I'm going to be doing some stuff that I haven't mentioned before. And then in the next few weeks, the videos will be coming out of like the last 3 streams that I recorded about other stuff. Yeah. Anyway, what's up, Afnan? Good to see you. Thanks for joining in. Hope you're doing well. Yeah, I'm super excited about today. This multiprocessor stuff is going to be pretty fun, I think. So yeah, the past videos will be the future posts, exactly. And so when these videos come out in the next couple of weeks, it'll be like kind of in the past, actually. It'll be behind the current state of progress in 31. It's like time travel, confusing stuff. All right. Is the audio working good? All right, cool. Let's dive into it. So today, doing Lab 4, Exercise 2, and I'll just kind of summarize real quick, like what's going on. So basically, the whole point of this lab is to get multi-processor, multi-core support working, eventually with preemptive multitasking, so we can have like different processes running on different cores, and they can preemptively, they can preempt each other. That's the long-term goal for the end of this lab. We have a long ways to go before we get there. The first thing we're just doing right now is adding multi-processor support to the OS. And that involves basically activating the other CPUs on the system. Right now we've been working on code that only runs on one CPU. Even if the system has a bunch of CPUs, I'm not making use of them right now. We're just running code on a single CPU. That's where the kernel lives at the moment. And what we want to do though is as soon as the kernel is kind of ready and finished initializing on the first bootstrap CPU, it can then go out and find any other CPUs that exist on the system and kind of wake them up, turn them on, and bring them online so it can run code on them. And basically this involves this thing called the local APIC, the local something programmable interrupt controller, the local advanced programmable interrupt controller. Each CPU core has one, and this is a device which you can use to send messages to other CPUs, do things like initialize them, or start them up, wake them up, stuff like that. So that's what we're going to be doing today. And basically, one of the key points also is the BIOS is pretty important for this process. Again, I'm doing all this like stuff on legacy, like a legacy system. So it's like a legacy PC system. And so we're still using the BIOS boot, I guess, method. And under BIOS, the information about all the other CPUs on the system comes from the BIOS. The BIOS places that data somewhere in memory, and then the OS can parse it and read it out to learn about the configuration that's available to it. Yeah, and a lot of that code is actually already written in JOS. I didn't need to write it, but we're going to make use of it. So yeah, just moving on to exercise 2. It says read some code to make sure you understand it. I've kind of already done that. That was like in these past episodes that will be coming out in the next few weeks. And the point of exercise 2 is to adjust our memory allocator such that it actually doesn't give out a specific page. So as part of the bootstrap process for bringing up all the other CPUs on the system, what we actually need to do is copy some bootloader code into memory and kind of wake the CPU up and tell the CPU to execute this bootloader code in memory. It's very similar to the bootloader that runs for this first CPU. It's a little bit different, but basically we need to do this. We need to place that bootloader code into memory, and we just want to be sure that we're not offering up that memory later on when someone else allocates memory, and which might clobber the memory. That's kind of the point of this thing, and I've already done that so far, but I haven't tested it yet, so that's what I'm doing today. So just to quickly, okay, here's the code. So let me clean up my VS Code a little bit. Too much stuff going on. Okay, well, it's totally clean slate. And what's pmap.c current. Yeah, what's up? The Squee 183 also Crawfish. What's up, man? Hello, I see you're working off of provided lecture. Is the building the kernel from the ground up, or does it give you basic code? It gives you basic code. That's like super important to me. I'm definitely not good enough to write the OS from total scratch, and so I'm working off of the basic code provided by the course. Yes. So I just used the course command, but it seems like the chatbot's not here today, unfortunately. Or maybe it's just very slow. But yeah. I'll also just, let me just link to my GitHub. So it's a little bit hard to find, but I'll link you to the archive that I've made of the OS, like the base OS that they use for the system. I've cloned it on GitHub to make it easier to find. Yeah, what's up, the Napalm? Which kernel can be used as a skeleton to build on top of it? This is a custom kernel. It's just like from scratch, basically. Yeah, yo, Pingu XOR. Yo, what's up? It's going good. It's going good. Another good day on YouTube. Working on some kernel code, doing some learning. How are you doing? Up to anything cool? Learning anything cool recently? Page init. So I was just kind of showing what I've already done so far. It's like the code's like kind of messy, to be honest, but basically this is the code that initializes the page allocator, and our goal is to have the page allocator know to not give out a very specific part of memory, which we are going to use to bring up the other CPUs on the system. And in particular, it's this thing called the MP entry physical adder. And basically all I did was add another variable here and add another check to make this particular page be excluded from the memory that the allocator gives out. And so by doing this if statement, we're not going to give out that page. And it says we can pass the updated check page free list. And I think, well, let me just run the kernel again, make new. Yo, Pingu, so this is a custom kernel. Yeah, Linux kernel is not involved in any way right now. Yeah, and also, what's up, Nirajan? Hello. Yo, what's up, SideQuest? SideQuest, yeah. talk to the audience, stay focused. I'm not sure I do the greatest job of that, but I try my best. Yeah. All right, kernel panic here. So I was already testing my implementation of this to see if I was passing the tests. Let me check 192. Yeah, so I added this panic here after the check page free list function. So this is basically the test case for the page allocator, and it's been updated with these new requirements that the page allocator does not give out this this specific place, this specific MP entry address, which we will use later. And I think what I'm just doing here is I'm just showing that I passed the tests. It succeeds, and panic on 333. So I'm actually not quite sure what happens if I run the kernel. Okay, I fail on some other assertion, but I think that's expected. It was just out of curiosity, side quest. Do you have multicore support in your OS? I know you were working on a kernel, but this is totally new area for me. But this lab is all about setting up multicore, and it's like tons of stuff I have no experience with. Yeah, I know your OS is pretty advanced, or at least from my perspective it was. It might fail the updated check current page dir test. I think that's what I'm failing right now on 1.23. Yeah, check page. Yeah, exactly. Yeah, yeah. No budget for that. Multicore is a nightmare. Yeah, no budget for that. Yeah. Well, I'm gonna try it anyway. Maybe it's gonna suck. Okay, so done with exercise 2. Question, compare current mp entry.s side by side with boot.s. Bear in mind that mp entry.s is compiled and linked to run above kern base just like everything else. What is the purpose of mp boot fizz? Why is it necessary here but not there? In other words, what could go wrong if it were omitted? Call the difference between the link and the load addresses we've discussed in lab 1. Let's take a look. Tree.s. So just to explain a little bit, boot.s is the normal bootloader. This is the thing that takes over from the BIOS and runs in real mode on the CPU and initializes the CPU enough and to a state where it can then load the kernel, jump to the kernel. So this is the main bootloader that runs on the bootstrap CPU, which is the first CPU that starts up. mp entry.s, on the other hand, is very similar, except it runs on the other CPUs, the other CPUs that start up later. They're called APs, application processors, and they also start up in real mode. And need to be initialized by the entry code, but it's a little bit different. So I've read through a bit of this already. And I'm just gonna make sure I got my break timer running. All right, good. Yeah. So first off, compare them side by side. What is the purpose? And specifically, what is the purpose of mp boot fizz? Let me see if I can answer that. Okay. So just to kind of orient a little bit, this is the entry point on both sides. It's start and start. They both start out with CLI or something for disabling interrupts. They both also zero out a bunch of the segment registers. The APs don't need to do the A20 line, so we don't have that part. And then after that point, what we do is we switch into protected mode. And to switch into protected mode, that requires loading in a basic global descriptor table. So we do the load gdt, which is declared just down here statically. It's just statically constructed at like compile time. np-entry.s does a very similar thing. It also needs to kind of level up from real mode into protected mode. It also has basically the same GDT, but the difference is it's with this linking stuff. So np-entry, so here's the difference. The kernel is linked to run in high memory at like hex F0, blah, 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 blah. And that means that all the functions and like global variables and stuff like this are going to be linked to basically be assigned at a high address, including the GTD descriptor thing. But on the boot side, that's not the case. The boot code is not linked like that. It runs in low memory. I think that's the reason. Yo, what's up, Landon? Hey, beginning something about x86 RISC. His genes are nice to look at from time to time. Appreciate the comment. Thank you very much. And yeah, x86 RISC sounds very cool. I would love to eventually do that one day. But for the moment, I'm trying to keep things just simpler for myself, because I don't know RISC-V and I do know x86, and so I'm just trying to make things a bit easier. But that's super cool. Good luck with that. So what does this thing do? Or np-bootfizz is some kind of conversion thing. Takes the address, subtracts the np-entry start, and then adds the np-entry p-adder. Interesting. I'm still kind of getting a little bit oriented here. I understand like the high level purpose of the macro. So this np-entry blob gets loaded into memory somewhere, and it's going to I believe it includes this thing. So this code needs to find its local copy of the GDT somewhere, but the actual location of this code in memory is not actually going to be known at compile time. It's kind of subject to the bootstrap processor. So here's the code that runs on the bootstrap processor. It basically copies what we see on the right, this np-entry stuff. It like copies that data into some place in physical memory, this hex that 7000 place, and then eventually it's going to pass that off to the other processors. And so basically, yeah, this code on the right doesn't know like what address the GDT desk variable is going to be at runtime. So basically it needs to resolve that. And the way it resolves this is by computing the offset from the np-entry start. Chill kernel having for fun. I'm so jealous. Love to be able to do what you were doing. Yeah, what's up? Motivation maxed out. Yeah. Don't be jealous. Yeah, just keep working at it. You'll get there one day. Just start streaming every week, and eventually you'll get there. So it computes the offset from the MP entry start to whatever this thing is, which is the G. So it basically gets the offset from the start to here, and then it adds the MP entry P adder. Yeah. I don't want to spend like too long with this, but I'll just try to map it out briefly. So here's memory. The MP entry.s blob gets loaded here, for example, by the kernel, which is at this like MP entry P adder variable, which is like hex 7000. And like at some point here, we're going to have our GDT, which is going to be in this blob, basically. And there's code that's running in here that needs to reference this and get the address of it. And the code that needs to basically get a pointer to it doesn't actually know at compile time where it will be. So what it does, let's just walk through it. It takes, actually, just out of curiosity, we can even maybe see in the symbol table of the kernel. Yeah, we can see in the symbol of the kernel the GTD desk symbol, because this whole thing gets linked into the kernel. So the symbol is visible in the kernel, and we can see that it's a super high number because it's linked into the kernel, which runs in high memory. So this number is super high, and we can't use that number in real mode. We need to convert this number to its physical address, which we can use in real mode because it'll be in low memory. And the way we convert that number into the physical address is we take that number, it's this S thing, big F number, we subtract the MP entry start symbol, which is here, also a big number. I might just do that just for fun and like absolute thoroughness. So basically we're taking GTD desk minus MP entry start, and we get hex 74, which is the offset from the start of this into here. And so if we were to update our diagram, it's kind of like here. And this distance, 74, this distance between the bottom and this thing is going to be hex 74. And the eventual goal is to figure out this distance from this line to the bottom of memory. And what we do then is we get this offset, and then we add plus MP entry P adder, which is this thing. And that's basically, yeah, that's how we find out this total distance from the GDT start to the bottom. We add this offset plus MP entry P adder. And then we can use that, physical address in this code. So that was kind of a long-winded explanation of exactly why this macro is needed. It needs to resolve this thing, which is a virtual address, and resolve it back into physical addresses. And we need to do that for anything, like any thing where we are referencing other stuff. Start 32, I actually don't really know what start 32 is. Oh, I'm stupid. Okay, it's right there. Okay, so that is just a long-winded explanation. It's necessary in here, but not there because this thing is linked into the kernel. This thing is not linked into the kernel. What could go wrong if it were omitted? If it were omitted, then specifically what's going to happen is the AP processor is going to be trying to boot up. It's going to be executing this code. It's going to get this extremely high address in this instruction, and that address is going to be outside the range that a real mode CPU can access. So I actually don't know what's going to happen, but it's going to not work. It's going to like crash or trigger some kind of exception maybe or something like that. So yeah, let's move on. Per state, CPU state, and initialization. When writing a multiprocessor OS, it's important to distinguish between per CPU state that is private to each processor and global state for the whole system. So this thing defines most of the per CPU state, including struct CPU info, stores per CPU variables. CPU num always returns the ID of the CPU that calls it, which can be used as an index into array like CPUs. There's a macro, okay. Okay, yeah. So besides the per CPU stack, you should be aware of per CPU kernel stack. Interesting. So every CPU has a kernel stack. Multiple CPUs can trap into the kernel simultaneously. We need a separate kernel stack for each processor to prevent them from interfering with each other's execution. The array reserves space for all those kernel stacks. To map the physical memory that boot stack refers to as the BSP's kernel stack just below case stack top. Similarly, in this lab, you will map each CPU's kernel stack into this region with guard pages acting as a buffer between them. CPU's zero stack will still grow down. Okay. So just for a quick look at the memory layout, we're gonna, So here's our current memory layout. We have our existing kernel stack. And we have, then we're not making use of these other things, but we're going to eventually map these blocks of memory to point to this memory that we've allocated in the binary, to where those buffers live in physical memory. Per CPU TSS and TSS descriptor. Okay, so in addition to having, and these kind of go together, the TSS is used to specify which kernel stack to use when handling an interrupt from user space. And if we're going to have multiple stacks, we're going to need multiple TSSs to kind of point to the different kernel stacks, I think. So we have all these TSSs. Okay, we're no longer using this global TS variable. Per CPU current environment pointer. So each CPU can run different user processes simultaneously. We can't just have one current environment pointer anymore. We need to have like an array of them or something. Current environment, the environment currently executing on the current CPU. Okay. Per CPU system registers. Interesting. So obviously each CPU needs its own copy of all the registers. And yeah, so we need to initialize registers. Okay. In addition, if you have added any extra per CPU state, performed any additional CPU specific initialization in your solutions to challenge problems, be sure to replicate them. Oh, interesting. I don't think I've done this. I hope I haven't done that. I don't recall. Okay. Exercise 3. Quick water break. Modify mem init mp to map the per CPU stacks starting at k stack top as shown there. The size is k stack bytes plus k stack gap bytes of unmapped guard pages. Your code should pass the new check. Okay, let's check this out. MP. Okay. Map the per CPU stacks in this region. Map per CPU stacks starting at k stack top for up to n CPUs. So who calls this? Mem init calls this now. So this thing maps the main stack. I guess it's called the boot stack because eventually all CPUs will migrate to their own stacks, maybe. Or wait a sec, maybe. No, I think I'm maybe misunderstanding it. Let me just go back. Okay. For CPU, I use. So I mean that is okay. Yeah, I actually think we're going to migrate stacks or something. So currently the CPU is running off of this boot stack thing, which is literally just, it's just an array. It's declared here. It's just like a region of memory, and apparently per CPU. Then apparently we have all our new stacks per CPU, and the CPU 0, the first one, will be running off of the boot stack, but I guess we're going to want to transition to this one later. So, all right, 20-second break, be right back. All right, so whatever, back here. Okay, for CPU, use this. Okay, just keep this for reference around here. So for int I equals 0, that's less than n CPU. Nice and easy. I'm going to boot map region current page dir, and okay, I need to specify a virtual address. I'm going to say VA size PA. I'm just going to copy this thing. So physical address is going to be I'm just going to make some variables one by one. So this is going to be the physical address that corresponds to per CPU kernel stack I pointer, I think. Let me just, this is, how does it even work? An array. Okay. Char per CPU kernel stacks. Unsigned char. I am being such a noob. I'm like, how do I even read this? It's, do you read it backwards? It's like, clearly the intent is that it is n CPU buffers that are each k stack size long. I am just going to assume it is the intuitive way I would expect. I think this is about, because I want to get the per CPU stack, but I don't want to like copy it. I want to get a pointer to it. Goes down. And it's divided into two pieces. It's top of the stack. Yeah, it's like the bottom of the actual stack, and then this guard page. But what I'm kind of curious, what do I do with CPU 0's kernel stack? Currently, this memory is mapped to the boot stack, which is currently being relied on for the kernel to like run right now. So if I were to do the naive thing, which would be like, okay, remap. Actually, I believe it is mem init. I believe it is being used. Let me just double check that. No, oops, mem init. So here we are. The boot stack is mapped to K, basically this just K stack top area, the CPU 0 area. But the thing is, I actually don't know which CPU is running. Like, I can't assume necessarily that the bootstrap CPU is CPU 0, I think. It might be something else. Okay, I'm getting kind of confused, but I'm just going to write the naive code just to kind of get something going. So the naive version of this is what? Size is always going to be the same. It is page size. We're going to, so mapping the guard page doesn't involve anything. So we're basically just we need to compute the address of this, like the bottom of each stack. And I'm just going to say stack. This is, okay, we start at stack top, and it's going to be stack, it's going to be k stack top minus, it's not like I times page size time, no, it's case, it's, no, it's k stack size. K stack size times 2. 1 for the, okay. I'm just gonna call this k stack chunk stack and guard zone size is going to be k stack size plus k stack gap. Is that right? What is this thing even? Oh, they happen to be the same, but whatever. Okay. What's up, Ghost? MB hoot Lova program is mind-boggling. Yeah, can definitely seem that way. It's just domain knowledge. Like, it can seem mind-boggling when you when you're very, very far from the topic, but for me, like, my face is like so pressed up against this topic right now where it actually makes sense, and you just need to get closer and closer and closer to the point where you're actually familiar with it. And I think that's kind of the case for anything. It's just a matter of, you know, you can understand really complex things if you just get closer and closer and closer to them. But if you're like too far away, it's gonna be just insane. Okay, k stack top minus n number of these chunk sizes of like both the stack and the guard. Right? It's like 0. The 0th CPU needs to go at least 1 down though. So maybe, oops, oh no, okay. K stack top. Oh no, I think I am right though, yeah. So for the 0th CPU, we want to be here, or K stack top minus, I think we want to be, I think this should be I plus 1 maybe. Yeah. I plus 1. So we want to go down one of these chunk sizes and then up k stack gap. Something like this, I think. Or whatever. What's up, Mad Flash? No, we are not in the Linux kernel right now. This is organic, homegrown, custom OS, GMO-free operating system. This is not an OS from big OS. This is a OS from small OS. All right. Okay. Yes. K stack top minus. Like if it was 2, for example, you know, for index 1, it's 1 plus 1 is 2 times 2 of these things plus state k stack up. I think that's correct. And my student I'm a student of life and operating systems, but not. I'm not a student of a university or anything anymore. Yeah, it's been a while since I have been one, but I did study computer engineering a while ago, so I do have a background there. But nope, I'm just a normal guy, normal programmer with a programmer job. Okay. Let's talk about size, permissions. It's PTW, I think. Kernel read write user none. Yep, that's what we got here. I believe stack and guard zone size, put it together. Yep. Please don't say you got a web dev job. No, that's true. I do not have a web dev job. Yeah, I don't have a kernel hacking job either, but I have something. Yeah, not a web dev job. I work in the music industry on musical instruments, like hardware devices. But I don't do kernel hacking there. Okay. So does this compile first off? No. Makes integer from, wait. Okay, I need some like casts or something. Does this work? Makes integer from, oh, okay, so I need, this is even pointer t. Okay, maybe I'll just even pointer t. Oh, whoa. There we go. It compiles, nice. Does it pay well? It pays decent. You know, I can live a pretty good life. I could make a lot more money if I worked in a different industry, but then I wouldn't get to work at this awesome job, doing very fun things. So, yeah, trade-offs. The code should pass the new check and check current pager. Let's try it out. Run the kernel. It did not pass the test. Also, but yeah, so I basically sketched out the code, but I also, how do we handle the boot stack? We're currently executing on it, but want to eventually migrate to the per CPU stack. How do we do this? Currently we're not, okay, so I tried my best, but it seems like this code is not working. Oops. Yep, this is the JOS code. Yep. Let's check out. Hey, what's up, Subnam? Background music. I'll link you to it. I use the same one every single time. It's the same lo-fi hip hop. Okay, so this is not working. It's unmapped guard pages. So let's look at this assertion. PMAP. Okay. Check kernel stack. Updated in lab 4 to check per CPU kernel stacks for each CPU. Isn't this quite similar to what I just wrote? Isn't this actually very similar? Oh, wait a sec. No. Yeah, base, and then they probably add base plus. Yeah, this is pretty much exactly what I wrote, I think. We have the k-stack top minus the multiplication between the iterator plus 1 times the sum of these things. And then I just choose to directly compute the address of the bottom of the stack, whereas they get this base thing and then bump it up. But maybe I actually did this wrong. So let me try that one more time. It could be I just don't really know how this pointer stuff works, although that didn't work either. 1134. So it's this thing, yeah. You know what? I think actually, yeah, I think that pointer thing was incorrect because so getting, dereferencing, indexing into an array produces an element of type of the thing stored in the array. And in this case, it is something of type char star, which decays into a pointer. So kind of think that should be correct, but seems like it isn't. But I'm doing basically the same thing. But it's possible that I need to like unmap boot map region. Actually, what is, I forget what this does again. I'm not sure what happens in the case that something is already mapped, which I think is the case. So I'm just going to add a cprintf. Oh, wait a sec, no. Okay, it's checking for all the pages, so n, let's get called n anyway, and then we're going to be checking for every single page, so I'm going to no. How do I use registers again? This is so annoying. What's in my register? It's in 0, right? It's like what? Quote 0p, right? Okay. And then I'm trying to print out the page offset by I'm just gonna XU maybe, or just X, I think. Plus that gap. Stack size. physical adder. Looks okay to me. So let's see which thing this. It might be the failing at the first one. Check. Okay, but check current page dir did succeed. So I don't know what is going on here. Oh, it's possible that it's failing in this separate call. Maybe. All right, 20-second break. Be right back. So it actually, this thing says it did succeed. So I actually think it might be failing. How do I find it? Core thing. Check that the initial, I think it actually is working. Wait, I'm just gonna panic. 4. It succeeded. I think it actually is working. I think it's failing for kind of a separate reason. Just curious if, yeah, definitely that's the case, I think. Or it's like maybe not. So for my own benefit, I added some separate consistency checks after setting up the virtual memory of processes. There's one call here. That does not matter. Okay, I'm thinking that if I actually comment this out, it's not going to fail. Good, okay. No, it's totally working. So it's totally working. Yeah, that just means that, delete this. Why don't you hop on Twitch? You'd find more people there. Dude, you think so? I tried it once, but no one joined on Twitch. And so I kind of just didn't try again, because I actually like YouTube a lot because they automatically archive all of the videos onto the channel. And I think Twitch doesn't do that. I think the videos don't last like forever or something there. So yeah, I just kind of didn't do it. Yeah, I've just been kind of trying to keep it simple and just sticking to one platform before I tried to like do different things. Yeah. Takes that more engaging community. Yeah. The new who's the T3 Linux guy? Okay. So this is going well. I think I passed that. The code in trap init per CPU initializes the TSS and TSS descriptor for the BSP. Let's check that out. All right, that's cool. Yeah, I don't know. Yeah, maybe I should. I just like YouTube. YouTube has really good statistics and they archive the videos, but I think double streaming would be an option. I think I would prefer to stay like native to like YouTube, but then also maybe double stream. Okay. So what's it saying? It works for Lab 3, but is incorrect when running on other CPUs. Change it so it can work on all CPUs. Should not use global TS variable. YouTube doesn't have emotes. Oh no. Too bad. Yo, what's up, Saksham? Hello, bro. YouTube recommended me your channel. Awesome. Thanks, YouTube, and thanks for joining. Okay, per CPU TSS. Thank you, appreciate that. Glad you are enjoying it. Are you interested? Do you do like kernel hacking? Are you interested in like low level programming? Have I heard of Tsoding? I think I have heard of that guy. I think he does like C programming and stuff on YouTube and whatnot. Okay, because Tsoding daily. It's correct if we are running on other CPUs because each CPU has its own kernel stack with code. Okay, so this code is like all buggy or whatever. Okay. Let me see if I can do this. It sets it up for CPU 0. How is it only specific to CPU 0? Because each CPU has its own, okay, because each CPU has its own kernel stack, right? And that's specified here. So we need to basically just set this up for each CPU. Trying to get into Linux kernel, really interested, nice. eBPF, oh interesting, that's cool. I actually don't know anything about eBPF. I've never used it personally, but I've heard that it's awesome. Okay. The CPU refers to the current CPUs and CPU info. We can get the ID of the current CPU by either this num thing or CPU ID. This CPU TS, rather than the TS, use mapped. The LTR sets a busy flag, so if you accidentally load the same TSS on one, you'll get a triple fault. If you set up an individual CPU's TSS wrong, you may not get a fault until you try to return from user space on that CPU. Okay. Let's start off nice and simple with our simple loop. As usual, going one at a time over all the CPUs. Oh, what happened? Okay. Are you doing labs or just customizing? I'm doing the labs. So I'm just like doing the class basically. I'm just doing all these different labs. Yep. And eventually it would be cool to customize it or something. But so for each CPU, we need to this CPU, what is that again? It's a pointer. This CPU UTS. So basically, wonder, can I yank this? I need to go to. Oh, what? My paste, the YouTube link. I need to. Let me try that one more time. Change. Control R0. Okay. Whew. And this is going to be wrong. We need. Okay. CPU stack equals k stack top minus I. So going back here, we need to, so 0, it's just simply, yeah, okay. I times k stack size plus k stacked gap. CPU stack top. Stack top. This is correct. This is correct, I think. We're not doing this anymore. Yeah. Yo, Mad Flash, just curious, how did you hear about JOS? I haven't met too many other people that have heard about it, so I'm just kind of curious. I think this is mostly it. We need to just set up. Then we need to load. Okay, so I guess we need to do this too. But what? But what GDT? Do we need no, do we need a GDT per CPU? Or GDT. Oh, so we have an array of we have so we have a GDT per CPU. Why is it? What's up with the +5? Is that new? No, it's just like I think, let me just go back to actually I'm gonna look at the GitHub quickly to see how it looks before. Oops. Yeah, so previously it just automatically computed the size of the array. And then now here we are manually specifying it. with some more entries. It says, okay. So that's how it works. GDT. Plus I. I need to give it a pointer. Something like this. Is that right? Each CPU info. It just has a CPU TS. And then don't okay. I think we need to do this also. So we basically set up a per CPU TSS, then a per CPU GDT entry that points to each of these TSSs. So I'm gonna get rid of this. No, right. I think this looks okay. Load. Do I need to do some magic here also? I think I might. Because get a triple fault. I think currently this is going to run on every single CPU, but what I'm doing is loading the task register for the same TSS onto each one, and I think I need to use each different one. And I think the way, so I need to compute these indices. Okay, so here I need to understand this better. Here it statically constructs the first like 6 entries. I don't know why it's saying 5 here. Because we need like 8. We need 8 plus 6, right? Okay, right, but we're already using 1. So it's basically 5 entries for the normal GDT entries, and then 8 for the per CPU things. I see. The only confusing thing is, so here's how we compute the index into the GDT. By taking this thing, shifting it down 3 bits. I don't exactly know where these things come from, but whatever. Taking these constants and shifting them down 3 bits. Oh wait, maybe I need to understand that. So 8 shifted down 3 bits becomes 1. but then this thing also becomes 1. KD, like don't, KT and KD, how, like don't, oh wait, no, I'm kind of, okay. No, we're basically just, yeah, this is like 8 shifted down, 3 becomes 1, 1, 0 shifted down becomes 2, 18 shifted down becomes 3. Okay, so it's like 1, 2, 3, 4, 5. And then the low 3 bits, I'm just gonna look this up, or maybe we had it somewhere around here. No, I'm not sure I ever looked up the GDT entries. Where do I find this? Predicted mode, management. Protection. Yeah, these are the GDT entries, I believe. 20-second break, be right back. Okay. Okay, I don't know. I know there's some the CPL, the segment registers. Like stuff is encoded in the low bits of the segment register or something like that. Okay, I don't know if I really want to go into all this detail right now, but yeah, whatever. Something along the lines of these are just counting up, and if you shift it down, it produces a simple index. So what I think I need to do actually, and I don't actually know for certain, but I think I need to take this thing, like, I need to get the index. I need to know the right thing to load into the segment register, or this TR register or something. It doesn't mention this at all, does it? Hints. If you load. I'm pretty sure it's wrong to just do this. The bottom 3 bits. Okay, right. So what I need to do is just take this times, shift it down by 3 to get the actual number. Need to wait a sec, no. Wait a sec, I think I'm not doing that. I think I'm actually doing this in a very flawed way. I think I don't need to loop, actually. This like is going to execute on every CPU. So I just need to get the CPU number. Okay. I kind of don't. Okay. All CPUs. Yeah, and then here it's just like times I. Right, this is getting kind of gross. So we need the GDT index. CPU index of TSS. It reads so weirdly. I don't know if that's better though. Okay, TSS, and then what we want to do is CGT masked back 3. I think that's correct. I think that's what we need. We cannot just be blindly pushing in this TSS value in for every CPU. We need to be computing the correct GDT entry like we were doing here. And the only difference is that we actually need to shift it back 3 bits when we're putting it into here. Something like that. Let's compile. No. Okay. Yet again, having all these issues. Pointer T. So that does compile, actually. I'm just kind of curious, who is calling this? So we call this on, we call this an MP main, that's where it gets called. We call it in trap init, but trap init only gets called from the main CPU, I think. Is that right? Yeah, trap init is only called from the main CPU, but then trap init per CPU is called on all the other CPUs via MP main. That makes sense. Okay. So we don't need this anymore. So let me see. Now what do I do? So I was here. I think this is correct. What is this? I think. Okay, yeah, we need to load these registers on every single CPU, including the IDT register. Okay. So what do I do now? Do I run the kernel or something? What happens? I panicked on the 3.3. Okay, what? Where's the 3.3.3? Okay, I need to not do that. Okay. But wait, CPU 0 found 1. I just need to check one thing, CPUs. Okay. Am I only passing one? Am I only doing one CPU though? I might only... Yeah. Okay, yeah, I'm only running with one CPU anyway. So, okay, when you finish the above exercises, run it like this. Moment of truth. Moment of truth. Does this, like, what happens if I do 4 CPUs? That did not seem to work. Okay, I think it might be my shell and CPUs 4. Let me try this. Moment of truth number 2. That also didn't work. It's still doing 1 CPU. All right, I don't know how, I'm just gonna say 4 here. Hey, Kimu. I don't know why it's not work. Please work. That still didn't work. What the? What is going on? Is it even getting the SMP4, right? It's passing the flag, like, Did this flag change in Kimu? No, it's I think this is there, like, right? So something isn't working. Could it be my code? This doesn't seem to be triple faulting. Okay, let's, I should see. Okay, here, okay, now I just need to figure out how to make this not say, this is crazy. What if I put it way at the start? Does this do anything? I did not do anything. What do I do? What do I do? I don't know. So it runs Kimu with Kimu opt, right? It's not really that complex. I guess I need to Google now. Q, SMP, not working. SP cores. Okay, maybe I need to. It says CPUs equals N. Maybe I really need to fully specify that. Okay. Let's try. For example, does this work? That did not work. SMP, CPUs equals 4. What do I need to do to make this thing run? Maybe I can just copy this quickly so I can just directly, oh wow. What about this? Does it fail? Okay. Okay. Cores. Does this do anything? That also didn't do anything. This is also 2016. Okay, I don't know. Time, I guess. Yeah, I have no idea why it's not creating new CPUs. No matter what I do. Oops. What if I like do 4x? CPU looks like an integer. So it claims, I don't know, it seems like it would be creating some CPUs. Okay, not good. Yeah, wow. And I don't think this is a problem with code that I wrote. Yeah, this would be kind of scary to debug. Like, it could be a problem with the parsing of the boot of the BIOS data. Okay. Got 4 CPUs. Enabled interrupts 1, 2. Starting. Okay, so this is not working. What do I do about that? How do I even debug this? It appears, maybe they changed something about QEMU since 2018. It's one of the downsides of following this old coursework is like it kind of bit rots a little bit. CPU hot plug. Wow. Two sockets of one core. One socket of two cores. Do I need to... What if I specify all of these parameters? I'm just gonna try this. I have no clue. Oops, nope. Does this do anything? That did not. Oh, CPU 0 found two CPUs. That kind of worked. Holy crap. What did I need to do? Okay. Which number two was it? Was it the sockets? Was it the cores? Was it the threads? All right. 20-second break. Be right back. All right. This is extremely exciting. Which number do I need? Is it the socket number? Nope. My terminal is fucking up. What is going on? Come on. What is that fish shell? Oh my gosh. What are you doing? This is crazy. Okay. This is actually... something doesn't want me to figure out how to run this thing. Okay. I'm gonna copy this back. One CPU. Okay. I'm gonna come back here. Copy in this whole piece of junk. That did work. What? Yeah, I think fish is... Holy crap, what just happened? All right, I'm just going to directly inject it here. And I guess this is how we'll do it. All right, does this do it? 4 cores? And okay, invalid CPU, whatever. Do all of these things need to be 4? Product of the... Oh, that's max. Can I get rid of max CPUs? Come on. Oh, man. What if I did 4? Four times... Okay, no, I think... Okay, let's get back to where it was working. Somehow this worked. Oh, I think it's just... Okay. Can I exclude some stuff? Does this work? That worked. 2 CPUs found. What happens if I do... But if I do 8, that is apparently ambiguous or something, and that produces 1 CPU. So I need all this extra stuff. What if I just do this? Does that work? That did work. What else can I omit? Can I omit this thing? I can. Well, okay, what can I omit? I think I tried this before. Can I omit the sockets thing? No, that's necessary. Can I omit the cores thing? I have no idea what I'm doing. I'm just removing stuff. And that actually did work. So if I say 4 sockets, oh shit, this should get me 4 CPUs. And now we're triple faulting. Incredible. Okay, well, that's not exactly what I wanted to see, but I am going to call that some progress. So this is what it looks like if your kernel has bugs. Okay, enough of that. So I'm gonna guess that's something to do with actually this thing, this LTR. And the reason I think that is because this comment said LTR sets a busy flag. If you accidentally load the same TSS on more than one CPU, you'll get a triple fault. And I think that was triple faulting. Let's just try that again. And so this time it triple faults even earlier on CPU 1. So that actually kind of indicates that this was necessary. Now, it somehow got to CPU 2 starting. So what should I expect to see? CPU 0 found 4 CPUs, then SMP CPU blah starting. Where does this starting message come from? MP main. And I'm just gonna cprint hello CPU. Okay, we made it through the first one, and then we print out CPU starting, and then we never even get here. Trap init per CPU. Oh, oops. So, okay, so we see XX hello, we get here something about this. We even get here, and I think we do not oh, oops. Wait, is it plus or time? Ooh, wait a sec. I think actually, yeah, no, this. It's a plus operator. Yeah, that would do it. Let's try that one more time. Yo, let's go. Hell yeah. Okay, no more triple faults. And we got a bunch of CPUs starting. I'm gonna call that a win. Can I get some W's in the chat if anyone's there? I'm gonna call that a big win. Always a bit of a scary experience when the machine starts rebooting like that, but all right. Crap, per CPU. Yo, thank you. Thanks, Illusion Man. Let's just see that one more time. So what we see, CPU 0 found 4 CPUs. Enabled interrupts 1, 2, I don't know what that means. CPU starting 1, 2, 3. Received page fault from kernel mode. I wonder what the CPUs are doing, actually. Like, are these other CPUs still running, actually? Not sure. Nice. Okay, what next? So, we made it through here. I'm gonna take the opportunity to commit, and I will also take so I'm just gonna bring this back and see if does this work? Expects an integer. Oh, oops. One more time. 8 CPUs. Okay, so that actually is working. So I can. So basically, I just needed to like patch this and fix the bit rot. Nice. Fix. Oops, V. .2.0. Okay. No more. Actually, yeah, I do want to get rid of that. Who added the panic? Whatever. Panic and okay, time to clean up some of this code. Okay. Does it work? Yep, that's cool. Very satisfying to see that. Okay. 2 each CPU's kernel stack, and CPU pointing at CPU's GT entry for the per CPU TFS. Yo, what's up, Front Forum Focus? Yo, what's up? So we got our 8 CPUs all going. That's pretty sick. Locking. Our current code spins after initializing the AP in MP main. So that's what these things do. Let me clean up my tabs a little bit. Let's see, MP main. Right, okay. So after the APs come up, they sort of signal, I guess, to the BSP, the bootstrap processor, that they are kind of ready. The bootstrap processor is like busy waiting, like spin waiting or whatever on this state. And after that, they just infinite loop, which is kind of nice. Okay. Okay, this is exciting. This is very cool. Okay, our current code spins after initializing the AP in main, in MP main. Before letting the AP get any further, we need to address race conditions when CPUs run kernel code simultaneously. The simplest way to achieve this is to use a big kernel lock. The big kernel lock is a single global lock that is held whenever an environment enters kernel mode. Okay, and is released when the environment returns to user mode. So this is like the absolute simplest thing. Whenever kernel mode is entered and we might be accessing some data structures, we're just gonna lock like absolutely everything. And so this is like the most naive way to do this. It's also the simplest way to do this. And the downside is that basically 2 programs running on different cores are kind of limited in their parallelism, because no 2 cores can be in the kernel at the same time. And so if one thread is running, makes this slow system call that's doing a ton of stuff in the kernel, another thread basically cannot make a system, like when the second thread makes a system call, it will just block until the other core finishes, which is not optimal parallelism. Yeah, what's up? Rained Kai, gained me, learned. Honestly, no idea what that means, but thanks for the comment. Rained key. Okay. Hold a big lock. This model environments can run concurrently on any of the CPUs, but no more than one can run in kernel mode. Spin lock, namely kernel lock. It also provides lock kernel and unlock kernel shortcuts to acquire and release the lock. You should apply the big kernel lock at 4 locations. Let's take a look. I'm a little bit actually disappointed that I didn't get to implement the lock, because I kind of really wanted to do that, but it is fairly simple, I guess. So we have the spin lock type. We have this global spin lock, and we have some functions for implementing the spin lock. Basically, a spin lock in the most simple and naive form is just like an integer or maybe even a Boolean or something like that. And you use atomic memory accesses to manipulate this and operate on it. What's this underscore thing for? I guess it's the init. But yeah, just for example, so to lock a spin lock, you first, I'm not looking at, I'm just trying to see if I just know it from memory, but like to lock a spin lock, you need to basically just busy wait on it to be free. So you basically say like if the spin lock is 0, then it's free. If the integer is 0, it's free. If it's 1, it's locked. And you do a busy loop trying to atomically like swap in a 1 into it. And if there's already a 1 there, that will fail or something, or I'm just gonna read it. If holding can acquire, yeah, while exchange. So if, okay, this is only for the debug, but yeah, we would spin on trying to exchange a 1 in there, and if the previous value, like these instructions return I think the previous value of what was there. And so we try to put in a 1, and if the previous value was 1, that means we just like relocked it and we didn't actually acquire the lock, someone already had it. But if the previous value was 0, we swapped in the 1, then we actually successfully transitioned it into being locked. And that's all there is to it. For unlocking it, we just atomically do the opposite, just unconditionally. Okay. And then so using that, we then have this lock and unlock function to lock the kernel as a whole. Normally we only, so when we unlock it, we would just unlock the spin lock, but what's this? Normally we wouldn't need to do this, but QEMU only runs one CPU at a time and has a long time slice. Without the pause, the CPU is likely to reacquire the lock before another CPU has even been given a chance to acquire it. And very interesting. It's like a QEMU specific hack. I wonder if like real kernels need stuff like that. Basically the concern is that under normal situations, there might be a lot of system calls or access to the kernel. So one thread might be in the kernel, one thread might be trying to start a system call to do stuff, but then waits on the lock. The first thread might finish its system call, and because QEMU has such a long time slice, that first thread could return from the kernel and then execute and then hit a new system call and re-enter the kernel a second time while the other one that's been waiting like just starves. So I think that's the issue there. All right, so what do I need to do? I need to add a bunch of locks in various places. Where would those places be? So basically on entering the kernel, basically via any kind of trap, I guess. That's where it's going to need to be done. It says on init, like lock before waking up other CPUs. In npmain, acquire the lock after initializing, and then call schedule to start running environments on this AP. In trap, right? Acquire the lock. In env, release the lock right before switching to user mode. Do not do that too early or too late, otherwise you will experience races and deadlocks. races and deadlocks, because we need to really be sure that basically as soon as we release the lock, it's no longer safe to just like access like kernel data structures anymore, because another thread, another CPU could have gotten the lock and now be doing its stuff. So you really need to be sure you're like not doing anything anymore in kernel mode after you release the lock. All right, let's try. So I'm going to i386 init, and we need to okay, your code here, lock kernel, easy. Okay, mp main. So now we're in the AP code, and we need to lock kernel, and then call it scheduled. Does this even exist? It does exist. Okay. In trap. We need to acquire the lock when trapped from user mode. So that is, oh. Did it already do it? Or what? I'm just gonna kill the bomb. I'm just gonna keep going. Reacquire the big kernel lock if we were halted in scheduled. Okay, that is interesting, but that's not it. That's like some other concern. Apparently a CPU can get halted and then restarted. I don't know what CPU started and halted means. I guess yeah, CPUs can like halt each other and stuff like this. So you need a lock there, but the one I'm more concerned with is this one. Yeah, what's up, Pranav? How you learn all this? This is insane. I mean, yeah, it is definitely a lot of stuff, but to be honest, I've learned like almost all of this just from streaming. I've just been like following this coursework every single week for like 7 months now or something like that. So I learned a lot just by following this MIT class, actually, pretty much. I knew stuff before, but I didn't know any of these like details before this. So all right, lock kernel. Yeah, totally. Yeah. Yeah, no problem. Jack's builds. You're also developing a kernel. Oh, awesome. What kind of kernel? Yeah, tell me more about it. Like, yeah. Oh, thanks for the sub. Appreciate that. Lock kernel. Satan kernel. Hell yeah. Yeah. Satan kernel. Okay, acquire the big kernel lock before doing any serious kernel work. Yeah, I'm just thinking about this deadlock thing. So if it's already locked and we call kernel lock, I think we're going to deadlock. Yeah, I think we need to be very careful to not try to lock the kernel if it's already locked by us. basically. Like you can't call lock twice. I think that's a pretty typical thing though for mutexes, I think. I'm just thinking back to user space. I think you cannot just call mutex lock twice without a deadlock. You need like a recursive mutex for that, I think. And the same applies for here. Like, but by default, you need to be very careful to not lock the same lock twice. Otherwise you'll deadlock. Did I set up the IDT? Yes, we have an IDT that works, can handle some interrupts. Yep. Yo, what's up, Raj? C is used for operating systems. Meanwhile, me who's using C for game development. Cool, that's awesome. All right. And run release the lock right before switching to user mode. And run. Is it here? I think so. I don't really know where I should do this. Should I do this here? CPU will be running for user space debugging. Kernel. I think this is okay because this is only accessing per CPU state. So that's not going to have races or anything like that. So I think I can do that right here. Yeah. My heap is block based. What about yours? I actually don't have a heap yet. All I have is a simple page frame allocator. Like this it's kind of like a pool based allocator using a free list, and that's it. I don't actually have a heap yet, so that's in the future for me. How to test if your locking is correct? You can't, but you'll be able to if you input the scheduler in the next exercise. Okay. Well, that was an exciting stream. Got through a bunch of, exercise 2, this question, read through on this exercise 3 and exercise 4 and exercise 5. No curiosity, I've completed my C course of 12 hours from YouTube, want to use C for embedded programming. Despite knowledge of every concept, I couldn't create a program for my own. What should I do? Start even easier than that. Just do some simple user space programming. Like just build some simple programs for yourself. Don't try to take on too much all at once. Just start step by step. So just do some simple user space programming, build some simple command line tools, and go from there, I would say. But all right, it's been fun, guys and girls, and anyone else. I'm gonna get going, but I'm going to drop my link to my Discord and just promote myself. Yeah, like, comment, and subscribe if you like low-level programming and what I'm up to. I stream every week, and I will actually be away for the next 3 weeks, but I have videos that are going to be released. So it's not going to be streams, but it'll be just pre-recorded sessions to keep the streak going. And all right, with that, I'm going to call it a stream. Thanks a lot for watching, and I'll see you next time. Peace.